I would like to start with thanks for the organizers of the conference to giving me opportunity to take part of the conference and also to speak about something. And what I will speak about in the first part, it will be related to church's thesis, at least in the way that we will use church's thesis, and then I will jump to another problem, which as we will see naturally emerges from the first problem I will speak about. So this is the outline, and so as you see, models then notations. And so for the first part, we know what is intended model for arithmetic. Is it really true? The problems we have, first of all, we have many models which have the same theory, but they look totally different, and they are not intended. But why they are not intended? We should have some good arguments for that. And what is maybe worse, plenty of models looks just the same. They are isomorphic. Still, do all these models are intended if they just look the same? So these are first doubts towards this statement that just n is an intended model. So, and I will ponder about this. But first, I would like also to make a distinction. Standard model is just a model we saw before, and this is a perfectly well notion. On the other hand, intended model, it's a kind of model which refers to someone, and this is the difference between these two notions, indeed. So the someone, I assume that the someone is mathematically educated. Otherwise, he could have indeed some unpredictable ideas of what natural numbers are. So this is the basic requirement. And the usual answer we get is just intended model is any model with omega type ordering. But this is just observation, what people say usually. And I will refer the work with Paula Quinon, and I will propose answer which narrows this broad class of omega type models. And indeed the work was done in two groups, but indeed, even if the groups started independently, there was some flows of ideas between the two groups, so it's really hard to say how these ideas mixed up. So I will just postpone this and I will not talk about this. And the references for this first part are like that. And so the starting point for us is the question, what are natural numbers for? And they are to count on them. Indeed. What? So, so if we count on natural numbers, we would say that intended model should allow us to count on natural numbers. And so what count mean? Let's agree that it is just addition and multiplication. Later we will ponder, we will think also about this, but for now, for this first part, let it be just like that. So then what is the output from these assumptions? What they can give us? So first, there should be named church in this talk. So here there is a place when you have church. So we use psychological version of church's thesis, and from this version we get that intended model should be recursive if we are to count on natural numbers of this model. Then we assume also that intended model should satisfy induction, and this assumption, of course, from one point of view, it's an obvious assumption. arithmetic is about induction, indeed. But I would say that one also could ask why induction holds. Is it something related to the very basic definition of natural numbers? Why do we? And of course we should have some arguments that induction holds, because otherwise why we would assume induction for natural numbers? And one explanation could be also of computational nature. If we adopt the computational definition of natural numbers, that it is just zero and the things we can get by applying successor and nothing else, then the induction just follows from this basic assumptions indeed. So we have some ways to justify why induction holds. And when we have these two assumptions, and we take the tour to the Tenenbaum theorem, which says that any model which satisfies induction and in which addition and multiplication is recursive has to be omega-type model, then we get indeed that, fine, intended model has to have omega-type ordering. There is no other way. So indeed, because of that, we get our thesis. What should be intended? What intended model should look like? Fine. Of course, it narrows the class of models, because not all standard models are recursive. Moreover, what are the other features of this? First, omega-type ordering is just a consequence. So we do not assume omega-type ordering, we just say we get it from computational nature of natural numbers. And also we get that the right notion of isomorphism between any two models is just recursive isomorphism. Otherwise it would be cognitively unacceptable for us. We wouldn't know that models are isomorphic. So once we accept, okay, so having this, we may ponder what we really get, what we proved. So if we accept the Turing explanation of computability with Turing machines, we know that this Turing machines works on strings, on words, finite words. So indeed, when we think what is the kind of object this intended model, it is just a Turing machine which computes success, or Turing machine which computes the universe. And this model is just the set of words which form universe and which are the notation for natural numbers, or the other way around. The natural numbers should be the notation for these words. So indeed, once we're done with this work, we think, okay, so maybe we should just concentrate on notations and ask, what are the properties of notations? What are natural properties, what not? And so this is why the second part of the talk starts. So from now on, we do not think about models, we think only about notations. So let me start with example. Assume we want to compute three functions on natural numbers: exponentiation function and a kind of binary addition and binary multiplication. So we compute by bits, not like usual addition and multiplication. And these are well-defined, useful functions. Assume we want to compute them. So what kind of notation we should use to compute just these functions? I would claim that it would be good, maybe, to write this sign of 0 crossed for 0. Then we may just write a in curly brackets for 2 to the a, and maybe we could just a sum b for a plus b, and so on. Why not? And indeed, indeed, when we think about natural isomorphism between hereditary finite sets and natural numbers, we see that these functions, plus bit and times bit, corresponds to set operations, sum and intersection. And so indeed, if we would be interested in computing these functions, a natural notation would be just the notation I stated on this slide. So indeed, it follows that what is the intended notation depends on what we want to compute on natural numbers. And when we get to this conclusion, we may say, okay, so indeed there is not so much that can be done because the notion of intended notation is somehow not explaining. We need something more. We need the set of functions we want to compute, and only then we may wonder what should be the best notation for these functions. But still we can work on that just by fixing some set of functions we decide they are important for us. So what will happen? First I will more or less state the ground on which we are. So notation would be just a function from natural numbers to finite words, and sigma of n is just a name for n. And the length of the word with u it will be with u in strokes. It will be the measure of complexity for us of a function, and we will require that the image of sigma is a computable set, a kind of natural requirement.
So you assume that you understand what is this definition?
Yes.
So all our problems are solved before. So now
Yes, maybe not all our problems are solved, but I would say let's concentrate on notations. Of course, we could, in principle. Yes, that's right. That's right. No, that's fine. But I hope we have more or less idea what is the model with omega as the universe. And then we say it's really a reasonable thing to think how we could deal with that just without omega, without natural numbers. Indeed. And one can wonder on or make some work to throw away this omega. And I think it may be possible, but for now I want to speak about some other things which may be also of some interest. So then we can define a notion of isomorphism between two notations. So if we have a function which translates the name of a number n from one notation to another notation, and in the other direction we may say these notations are isomorphic. And if a function is polynomial, then these notations are indeed quite close one to the other. If we compute by hands, of course, it does not mean that they are the same for us. But if we use computers, they are not so far apart. Indeed. And indeed, nowadays, maybe it's more important to define notation which would be good for computers, not for us, for calculating something. Okay, so then what does it mean that the function is computable? Function on natural numbers. So of course we can get to natural numbers only by using names for them. So we may just translate a relation into the relation on strings using our denotation function, and then we say that a function is recursive if it is recursive with respect to this translation. If it is recursive as a function on strings, not on natural numbers, which are abstract object. And although we do have some explanation what recursivity means with respect to natural numbers, we have this recursive definition of this class starting from basic functions and some schemes, minimum operation. But the basic notion of computability comes from Turing machines. Let's say this is our assumption. So, yes. So of course, and when we want to justify that, for example, the Grzegorczyk classes gives us recursive functions, or just the usual definition of a set of recursive functions gives us what we want, we usually refer, we can compute all these constructions, but compute meaning with respect to some natural notations for natural numbers. So indeed, in justifying that, for example, Grzegorczyk's classes are recursive classes, we would refer to our intuitions of computing. So first, in the first part, I will look on the level of recursivity, and then we will step down to polynomial time functions. So Paula already said a few words yesterday about this work. So, so when we are interested in notations which are just recursive, so Shapiro already observed that that if we just took any notation with a recursive image, then function which is computable with respect to any notation is just very small set of functions. So indeed, we do not capture our intuitive notion of recursivity with that. On the other hand, if we would say that function is computable with respect to some notation, we would get two large class of functions, functions which are highly ineffective. Maybe not very high, because we have also an upper bound on function which is computable in some notation, but anyway we get something too large. So, however, we have the following equivalence, so that it is enough to require that successor is computable, and then we can capture the usual notion of recursivity for natural numbers. So this may be considered as an explanation what we need from notation, and that we need successor to be computable. And the second point, I think, is so obvious that it is not mentioned in the paper, but we will look at this point in the context of smaller complexity classes. So I put it here also, and of course we can have notations which are much worse than binary notation, which do not allow us to compute all recursive functions. So indeed, the choice of notation is important. So if we accept this principle that acceptable notations are just notations with computable successor, then it is very fine, because we have very weak requirement, just successor should be computable. And we already defined the class of recursive functions. So from requiring very small amount, we fixed the large class of functions. On the other hand, if we think about in terms of intended notations which are more or less suitable for us or for our computers, this is maybe too little, because two notations which are recursively isomorphic still can differ very widely. I would say even polynomially time isomorphic notations could differ, but we will see in a moment how is it on the level of polynomial time computations. So I will restrict my attention to some set of notations. So let notation be dense if codes for natural number n is not very big with respect to the length of this code. So the usual notation for natural numbers have this property, and this property expresses something like efficiency of our code. Simply, we do not write too long expressions to denote small numbers. And indeed, if our notation would not have this property, it could happen that we could not just store the input or the output of a function. So indeed, it would be not a difficulty of the function itself, but just the problem with not having enough memory to store the input. So we want a notation to be efficient in this way. And I will say that notation is also regular. If we do not have only the upper bound on the length of the name, but we have also a lower bound. So it's not the case that we can have a big number with a very small name, very short name. And this requirement seems to be reasonable with respect that our notations usually are like that. But on the other hand, one can wonder, so what if we have big number with a small name? Better even. So this is why I do not impose this condition, and I also remark that usually we have this condition even in a stronger form, because if we require that the length of our notations grows in the size of numbers, we could infer this condition. But let's do not require it just now. So the main observation I want to speak now is that we do not have a notation which is both dense and which would allow us to compute more functions in polynomial time. So indeed, this can be read in that the binary notation is in a sense maximal if we want to concentrate on polynomial time functions. We cannot have a better notation when we consider polytime computations. And from the proof we will also get that any two notations which compute the same set of polynomial time functions are also polynomially isomorphic, but this is just remark based on the proof. So what this means? It means that indeed, if we just fix this set of functions, we cannot do better than in binary notation. We cannot have more. On the other hand, it is not so hard to show that we can have various sets of polynomially time computable functions when we have different notations, and we will see why in a moment. And as I said, any two notations which compute the same set, which being poly, are isomorphic. So let me say a few words about proofs. They are not hard, but maybe they are illuminating. In a sense, they show why this holds. So the theorem is on the slide, and so let us assume that we have a dense notation, and that this notation computes all polynomially time computable functions. So among these functions are, of course, remainder modulo 2, the floor function. For an integer it will be just identity function, but it should be really x divided by 2 and then take a floor of it. So then it is polynomially time computable. And then one may show easily that if this set of functions is computed in polynomial time in notation sigma, then indeed we have polynomial translations between sigma and binary notation, but polynomial in the length of the binary representation of n, so in log n, and the function is just a natural translation using this dividing by 2 and checking what is x modulo 2. I wrote the algorithm just because I wanted to stress that if our input is in sigma notation, then we have no guarantee that the time of the algorithm will be bounded by the length of sigma of n. We know that we will iterate the loop log n many times, so it will be polynomial in the length of a binary notation, but sigma can be a wide notation. We do not know what it is. However, yes, so this is, so we iterate loop log n many times indeed, and so if sigma would be regular notation, we would have two translations which are polynomial time, in polynomial time. If sigma is not regular, then this translation may be polynomial in the length of the output, not in the length of the input. So it's not as good as we would like, but for regular notations, we can already state that if a regular notation sigma computes just these four functions, then it is just polynomially isomorphic to binary notation, and of course it computes the same set of functions in polynomial time. So for regular notations, we described that set of polynomial time functions is maximal. But okay, notation needs to be regular or not, and we show that we will see that indeed if notation sigma computes all polynomially time functions in a sense of binary notation, then it has to be also regular notation. Why? So assume sigma is dense and assume bin poly is included in sigma poly. So by contradiction, let me assume that for any C we have infinite set of numbers with which codes are just smaller than log n to the 1 divided by C. So this is just negation of regularity condition. So we assume this, and then it can be seen that in this case we would get a kind of speed up which is impossible. Speed up for binary notation. So let me take the set of functions which are in a sense hard. So indeed there are such functions such that they diagonalize against any functions computable in time n to the k, and diagonalize in a strong sense, namely there is no machine in times n to the k which would agree with functions hk on more than finitely many inputs. And the function hk itself is also computable in polynomial time, even in n. There is log n and there is n to the O of k. So it should be just log n in both cases, indeed. So indeed, these functions are computable in polynomial time, and yet they are very hard for time k and log n to the k. And they can be defined just by usual diagonalization method. So what kind of speed up we would get then? Since our notation includes all what is in bin poly, then of course it has also these functions computable in polynomial time. So let me take S, which is exponent in the time of the running time of the algorithm, which computes function hk, but on the notation sigma, not binary, of course. Then let me take this infinite set of natural numbers which has short codes with respect to notation sigma, and let me take k, which is such that translation between sigma and binary can be done in log n to the k. And of course, because as we said, translations can be done polynomially in the length of the output. So indeed, we do have translation polynomial in length log n to the k. So then what form of speedup we would get? We would get, so we have this hk functions computable in time log n to the s in notation sigma. We have these numbers with shortcodes. So if I would like to compute h of k in binary notation, I would simply translate the number to the sigma notation, compute the function on sigma, and then I would return the output, translate it again to binary notation. And the working time would be the cost of translation, then the cost of computing the function in sigma notation, which is the length of the number to s, and then translating again. And if our input is one of this ai, then the cost would be log ai to the k, then the length of the translation to s, but the length is small. So it would be just log of ai, and then the length, and then the time for the another translation, which is also just log ai to the k. So summing up, we have an algorithm which works in time log a to the k, and which agrees with our hard function on infinite set of natural numbers, what is impossible. So we get a contradiction indeed. If we could have numbers with shortcodes, we could compute some function in binary which we cannot compute. So indeed, because of that, we can infer that sigma has to be regular if sigma is to compute all functions which are bin poly, so which are polynomial in binary notation. So let me discuss a bit about these results. So what we get? We get that if sigma is regular and computes some very basic functions, then it is just as good as binary notation. So indeed, we somehow pinpoint the set of polynomially time computable functions and binary notation if we restrict to regular notations. Then we have no choice if we just have this four easy computable functions, which we really want to be computable, because they are very basic functions indeed. There is even no multiplication in general form in this set. On the other hand, and it can be dug out from the proof indeed, that if we have this for some dense notation, that these four functions are computable in polynomial time, and if a function f is computable in this notation polynomial time, but not in binary in polynomial time, then indeed the only reason that this function is not computable in polynomial time in binary notation is just that the output of the function, the values of functions, are too big. If there would not be as big, if there would be a polynomial bound on the length of the output, this function indeed would be computable in polynomial time in binary notation. So this is the only irregularity we can get from a notation which is not regular. But what we get more, we got also that if a notation is not regular, then for sure there exists a function such that this function is computable in polynomial time in binary notation, and we cannot compute this function in polynomial time using notation sigma. So indeed, if we agree that we want all polynomially time computable functions to be polynomially time computable in notation sigma, then we have no choice. We have to pick the notation which is polynomially isomorphic to binary notation. So indeed, this is somehow an argument for binary notation, maybe. However, we indeed have many other notations, and just like one notation we saw before, we can just write powers of primes in all this notation for natural number a. We know, but now we know that some functions which are polynomial in binary notations are not polynomial in these notations, just because these notations are not regular. We have short codes for large numbers in these notations. However, I would hesitate in saying that this is an argument that we should just use binary notation, of course, because first of all, how we should justify that this is the set of functions we want to compute. First of all, in the proof we used some very strange functions, diagonal functions, and in practice we do not use such functions indeed, rather, usually. Of course, it is a robust class, but do we need all of that? And even if we have some independent characterizations, these characterizations depends heavily on the structure of binary notation. And moreover, I would personally believe that it is not the case that we should always stick to binary notation and computing just polynomially time computable function in this sense. First of all, we use various notations, like notations based on Chinese remainder theorem, for example, this notation of prime power. So for various tasks, indeed, we need some notations which are, and in these notations, maybe some functions which are easily computable for us in binary are not easily computable, but some other functions will be easier or will be computable more easy. For example, if we have this prime power notation, then multiplication would be computable in linear time. And addition would be harder, I guess. So if we would be interested only in multiplying two numbers, this is the notation. If we know, for example, that we will do many multiplications, it would be even more profitable to translate our inputs to this notation, perform all the multiplication, maybe exponentially many multiplication, and then if we would like to, we could translate it back to binary, if we would need. So indeed, what is the notation we should use depends on what we want to do with the numbers, indeed. So I wouldn't say that binary is just the notation and we do not need another notations, but indeed it has some interesting features with respect to natural class of functions. So okay. So, but also the above the proof and theorem can be restated also for other complexity classes. So polynomial time is a large complexity class. There are some serious doubts whether this is a class of effectively computable functions, but indeed we can reprove something like that also for some smaller complexity classes like quasi-linear time, just because also in this class we can diagonalize and we can have this set of hard functions. So it's not just about polynomial time that binary notation is maximal. Yeah. Okay. So what should be conclusions I would like to state? First is that under some weak requirements, we got that we cannot get better than binary, indeed. Even notation is regular. And if a notation is just dense, but maybe not regular, then we know that we cannot get more functions which are computable in polynomial time in this notation. So this was obvious in the case of recursive computations. In polynomial time, probably we would need a justification like that, which is not complex, but anyway, it's needed. And what's more, so if we assume that a notation is dense, and if we want all functions from being poly to be efficiently computable in this notation, then indeed we know that we cannot do better than in binary. Of course, there is also a problem how complex is translation function, but I do not want to go into the problems of whether p-time is really feasible or not. Okay, maybe one more remark. We have this various notations like ST, and we can formulate, for example, we can define a recursive characterization of p-time functions for binary notation by Cobham or Cook and Bellatoni did it. And now we know that we have many notations. This notations computes many different sets of polynomially time computable functions with respect to this notation. So maybe the question one could pose: could we construct such recursive characterizations of polynomially time computable function, but with respect to other notation, like set theoretical notation? What should be a recursive schemes for computing polynomially on sets, not on natural numbers? So yes, and also with respect to other notations. And yes, so that's all. Maybe I hope you enjoy, and it was, yes, maybe it was inspiring also.
Thank you so much. No, you keep. About your notion of intended. So there are different intenders, agents. What intended means there exists one agent that intend, or they all agree and they intend the same thing? Or what do you mean by intended?
Yes, so for the formal part, I would say that intended means all polynomially time computable functions should be polynomial time in this notation. But of course, it depends. It depends, because intended for us, for a human, would be, I want to easily compute some functions like addition, multiplication, maybe something more. But for another man, for another task, it would mean something different. So I would say we can live with this various notions of intended for various purposes, various tasks. If we fixed this one, we would get that binary notation is maximal. But if we would be interested in functions like bit or and bit and, we would have another notion of intended and another intended notation because of that.
Why to bring this psychology? Suppose I intend and then I got sick and I keep intending. Should I finish my intending in finite time? Well, these questions arise. What do I intend and how, and whether you understand my intention, how do I convey my intention? Why do we need this problem?
Why do I say intended? Of course, I'm not supposed to know what your intends, but at least what I intend from from notations, it would be something like that. But I do not know whether you can find a better description, better word for that.
Constraints.
Constraint.
Yeah, mathematicians spend centuries to cleaning up language.
Yeah.
Drag them
maybe
back.
maybe constraint would be, but then there would be a question why to get such constraint.
Sure.
Yes, and
we can discuss
so
different.
yes, so usually you get something like why to take this definition and not the other one. Yeah.
No, intended is a pragmatic term. I think that it shouldn't be understood strictly psychological, but there is one. I remember there was an interview with Zofia Krygowska, who was probably the most important Polish specialist in teaching of elementary mathematics. And she said that one schoolboy came to her, not educated mathematically, and said, "Oh, I made a discovery. I found a rule or theorem that every next number is greater by 1 from preceding number. And it shows that it is a very natural constraint, that it is of course it is not recursivity and not natural order, but a regularity, which is. And second remark is that Russell, for example, in Introduction to Mathematical Philosophy, when he developed Frege's approach to natural numbers or sets, he says that he doesn't recommend teaching arithmetic by this method because logical and psychological is not parallel. Psychological constraints or whatever you call this appear earlier than logical analysis. I think that this idea of intended model is psychologically supported. It is something less than standard model.
Yeah, thank you.
Thank you. So I intended initially to ask about the intended model, but now I will maybe give some clarifications about this notion or how it was used in this Tenenbaum part that you mentioned at the beginning. So the starting point was to take kind of psychological approach and say that people want to compute on natural numbers or want to perform at least addition and multiplication, and then with Tenenbaum we realized that this notion can be given a more formal definition, right? And that we defined the notion of intended as the recursive omega order of piano first order arithmetic, right? And the same situation happened with a standard model of arithmetic, right? The standard where there is just an omega order. When you take, for example, the work of Montague from 1965, where I don't like say it's the first place. It's the paper where the notion appears, and it seems to be one of the first places where it is discussed. He says that standard model of arithmetic is the model that first comes to the mind, right? And after he gives a second order definition of what it is. And so one can see that in this paper it goes from psychological to formal too. Yeah, so these are the explanatory part of my intention, and now I would just to try to understand what you did with defining what the intended notation are or what they can be. So you put the additional restriction or on the notion, right? So we have this notion of standard model, the notion of intended model. They are both formal at this point in history, and now you come here and you say, okay, so we can do more, right? We can make an additional restriction or what an intended model is, right? Is that your
In a sense,
point?
yes, but of course, in this second part, we just assume that the model is omega type model, and we do not care about what is the complexity of adding addition and multiplication in the non-standard models, which also may be recursive if we want just one function to be recursive, just addition, for example. So we fix omega model, and then we look for another restriction in that, like efficiency.
Thank you for giving me this second chance. I just recalled a particular intention. It's due to quite well-known logician, Yesenin Volpin, and he intended the following natural numbers: World War I, World War II, and here we are.
So this is ultra-finitism in that.
Yes, but this was historical intention of a very intelligent man. Now, deal with it.
Okay.
I would like to separate between the mathematical content of your talk, which is very interesting because I think the topics of the dependence or notation of complexity is important, and the motivation you gave at the beginning. First of all, intended models are intended to do models of something, some theory. Theory is a list, is a set of axioms. Axioms are formulas. Any definition of formula that I know is either recursive by some induction, or as a finite list of symbols. So it assumes already the natural number. So you cannot even talk about theories without understanding first the natural numbers. So all these kind of things that people understand what is a formula, they understand what is a proof in the axiomatic system, they understand what is a recursive function to the point to say that the intended model should be recursive, and they pretend they don't understand natural numbers that lie below everything of this. Without them, you can understand nothing.
Yeah.
Second thing, as you said about, you say that you don't want to compute a natural number because they are abstract, so you compute with strings. I keep hearing this, I'm always amazed to hear the strings are not abstracts. First of all, strings are a list of symbols. If you allow, doubt maybe list can be of finite, when the finite number comes from some non-standard model of arithmetics, then list is far more from abstract than the natural numbers, because it's, and list, is the distance between two symbols important or unimportant? Should it be exactly the same line, or maybe are the same list? And symbol, what is a symbol for God's sake? Is the letter I of the English alphabet, I mean not a capital, the lower, is it a symbol or not? It has two parts. When I write two symbols, one after another, do I really write the same symbol? Are they really identical? Symbol is something very, very abstract for itself. And at least a symbol is abstract to the square or to exponential abstracts. Now, it is not something less abstract than natural number. If at all, it already depends on the natural number. Unless you think geometry is completely something non-abstract, concrete. Things, continuity, etc. But this goes against all the understanding of discrete.
Fine. So I would say that indeed there are 2 points you mentioned, and maybe for the second point, I would argue that our intuitions, which corresponds to efficiency, computability, they come from indeed the physical machines, what they do indeed. So these machines, they do not work on numbers. They work on strings of bits or some other inputs, but these inputs are given to them just like finite words. And of course, there is a problem how they identify 2 digits as the same digit. But we say, okay, if electricity is like that, it is 0. If it is above that, it is 1. So we can, in practice, we can handle and we can identify the symbols with 0 and 1. And of course, if the voltage would be, let's say, half, then it would be random, but we take care not to fall into such situation. So indeed, when we have this intuition, saying that something is computable just on natural numbers and it's efficiently computable, it means nothing unless we can express it as computable on words which denotes these numbers. And in practice, we have these problems. If we want to make a mathematical theory out of this, then of course we need to define in abstract way what is a finite word, what is alphabet, and so on. But this is just to make a theory out of it and to investigate the notion of computability. But the intuitions comes from just this very basic computing machines and even computing on paper and pencil, with paper and pencil, like in Turing, first definition of Turing machine. Also abacus. Yes, I would say also compass and ruler gives us some notion of computability. So everything we can present in algorithmic way. So this is just the notion of discrete computations indeed. And with respect to the second question, that we need notion of natural number, we need all of that to define this theory. So maybe one answer which I would not subscribe to this, but it is possible detour, it would be, okay, let's start mathematics on strings, on words, not on natural numbers. Then you can indeed develop mathematics with word as a basic notion. So you could. Yes, but you can define induction also with respect to words. You can define induction on words, which would be a bit different. You would have, let's say, two successors and so on. It's the same. Yes, I would say it's the same. But this is, I said that I would not subscribe myself to this answer, although I believe one could perform argument in this way. But I would say also, I do not want to define mathematics just from the basic assumption. I do not want to be a second Frege or Cantor. I just want to investigate what the world is like using the all mathematical machinery I have. If I would need to use large cardinal axioms, I would use it without doubts. Maybe just pointing that this is with this assumption only. So maybe it's not so certain. But it is a different task to explaining and to defining something from the basic notions. And I want just to explain, not to define mathematics as a whole. This is, yes, my answer.
Thank you so much. Let us thank our speaker once more, please. This is obviously the last session of the plenary meetings. And I have to say that I've found up to now the meeting very stimulating, and I'm sure it will be also in the afternoon session. And I wanted to thank the organizers, and particularly our chairman, for bringing us together and providing such a hospitable atmosphere for real interaction and a very pleasant time. Thank you very much.